Number 40. Predict the valence electron molecular orbital configurations for the following and state whether they will be stable or unstable ions. Okay, and in this case we have magnesium 2 with a 2+ charge. So we're trying to basically make a diatomic molecule of 2 magnesiums with a +2 charge. And let's see what's going to happen. Well, we need to find a molecular orbital configuration. This comes from your valence electrons. So first, let's just find out how many total valence electrons we have in Mg2 2+. Now, keep in mind that magnesium, right? If I look on the periodic table, magnesium is in group 2. So that's going to come important. That's going to be very important in a little bit. But it's important here because, remember, group 2 has 2 valence electrons. But we have 2 of them. So if I have 2 magnesiums and each one of these has 2 valence electrons, I'm going to just multiply it by 2 valence electrons. So right now, the total that I have is a total of 4 valence electrons. But can't be that simple. They tell us that we have a charge here, right, of a +2. And plus means always that we're going to lose 2 electrons from our total. So in this case, I'm just going to subtract 2 electrons. And 4 minus 2, that will give us a grand total of 2 valence electrons to work with. Okay, beautiful. This is going to come in handy when I'm actually going to draw the molecular orbital diagram. All right. So, what's going on here? Well, it's a whole mess, right? But basically, these are your generic molecular orbital configurations depending on what group you're in. Now, we already discussed that magnesium was in group 2. And voila, group 2s follow this valence electron molecular orbital configuration. And just know that the difference here is between the mixing of orbitals between your S's and your P's. Now, to get actually into that is way above a Gen Chem course. That's like higher level chemistry. If you're majoring in chemistry, you'll dive into that. But for right now, just know that these are the 2 general forms. And since it's in group 2, I'm just going to pull this one up because this is the one that we're going to use. We're not going to use the other one. So we could basically just like, I guess say bye-bye. Bye. But just know that, the other one is for those other groups. So I have Mg2+, and we're getting into it. Now, I did put markers down here. As you can see, there's blue and yellow highlighter. This is just dependent on what S and what P we're in. Basically, in this case, it's going to be the period. So magnesium is in group 2, but it's in period 3. And for period 3, that's going to be your principal quantum number. So you got 3s. 3s. So if we just kind of match them up, we got 3s, 3s. And then all these would also be 3. So 3py, 3pz. These are all the different types of orbitals. 3px, 3py, 3pz. Okay, cool. Now just know that for every bonding orbital, keep in mind that this is sigma. So these are your sigma bonds. And these are your pi bonds. For every bonding orbital, there's an antibonding one. You see how these are basically identical to each other, but one has a star and one doesn't. The star is always the antibonding. And for every bond that you make, you will always have an antibonding equivalent. So for example, here's this set of 2 bonds, and there's the antibonding equivalent, and the same thing goes for these. Just know that as you go up the ranks, you're increasing in your energy. But in this case, we only have 2 valence electrons. So we have to put those 2 valence electrons basically in the bottom. So just like electron configuration, you're going to put your electrons in the upper right-hand corner, right, of each parenthesis. And each parenthesis, for each orbital will say you're only allowed to have a max of 2 electrons. So for your first one, here's your sigma 3s, right? Your total valence electrons would just be 2. I have to fill this one up before I go to this one. And now, how many antibonding orbitals, electrons are in the antibonding sigma orbital? 0. And basically, all the other ones would also be 0, because the total amount has to equal those total valence electrons. Now, for a complete answer for the valence electron molecular orbital configuration, you only keep up until you have the last number. So since we have 0 electrons in all these other orbitals, you could basically get rid of them. And that's what I will do. So, goodbye, toodaloo. You could also, pause the video if you need to write it down, but bye-bye, it's leaving in this case. So, in this case, we found out the valence electron molecular orbital configuration for this one. Now, we just have to state whether that will be stable ion or unstable. And this comes from the bond order. So, if they're asking for whether you're going to form an actual molecule between 2 magnesiums, you need to know the bond order. And the bond order will specifically tell you what type of bond will be made between the 2 magnesiums. And the formula for a bond order is this right here. It's pretty simple. Bond order just equals your total number of bonding electrons minus the total number of antibonding electrons. And that's divided by 2. And you can only do this if you know your valence electron molecular orbital configuration. So, let's go for it. Bond order equals, well, this one's pretty easy because you only have one, right? You only got one molecular orbital. And since there is not a star here, remember the stars are the antibonding. This is technically bonding. And how many electrons are in the bonding molecular orbital? There's 2. So the number of bonding is 2. Number of antibonding, there is none here, right? We got rid of all those zeros, so this would be 0. So in essence, your bond order is going to be 2 minus 0, and then that's all divided by 2, right? Oh boy, what happened there? How did that was magic. Let me just pull this up. So 2 minus 0 is 2, right? 2 divided by 2 is 1. Okay, well what does that tell me, right? We have a bond order equal to 1. And a bond order equal to 1 means that we are going to form a single bond between the magnesium and, between the 2 magnesiums. So if you have a bond order that's greater than 0, basically, you don't want a bond order of 0. But if you have a bond order greater than 0, you have a stable ion because you're actually going to know what type of bond is going to be made. So, in this case, it is going to be a stable ion. And that is the answer to this question. What'd you think? I hope this helped. Let me know in the comments. Thank you so much for viewing the video. Subscribe to the channel, and I will talk to you all later. Have an awesome day. Keep studying hard. Talk to you later. Bye-bye.